that you yourself proposed, it's ASCII, the American Standard Code for Information Interchange. And indeed, it was a bunch of Americans years ago who came up with this system. Unfortunately, at the time, they only allocated 7 and eventually 8 bits total for representing letters, both uppercase and lowercase, numbers on the keyboard as well, punctuation symbols as well. And so per our conversation a moment ago, if the Americans in this room, so to speak, only used 8 bits total, how many different characters can we represent with a computer in this story? So only 255, technically 256 if we again start counting from 0. So that's not nearly enough but it is to represent all human languages, but it is enough to represent at least English among some others. So here, for instance, is a chart of the ASCII mapping. And sure enough, if we zoom in on like this column here, 65 is capital A, 66 is capital B, dot, 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 72 is H, 73 is I, and so forth. So there is a standardized mapping for at least all of these English letters. Well, suppose you were to receive an email or a text message or like a Google Doc containing this pattern of zeros and ones. So 0, 1, 0, 0, 1, 0, 0, 0, and so forth and so forth. So 3 bytes worth. 3 sets of 8 bits, that is to say 3 bytes, each of which represents a single letter in ASCII. What message have you received? Well, I'll do the math this time so we don't have to. Suppose what you really received was decimal 72, 73, 33. What message did you just receive? If you recall the previous chart. Hi was in fact correct. Why? Because H is 72, I is 73, and wait a minute, 33. So here's H, here's I. 33, if we highlight it instead, happens to be an exclamation point. So like that is literally what is going on underneath the hood, so to speak, when you get a text message today that literally says in all caps and an exclamation point, hi. Your phone has received at least 3 bytes, each of which represents a letter of the alphabet. Your computer is quickly doing the mental math to figure out exactly what numbers those are, and then looking up in the so-called ASCII chart in its memories, in some sense, what letter should you actually see on the screen there. And so if you were to then display that message, you would see it indeed in English as opposed to those numeric equivalents. How else might we use this then? Well, here again is that chart. And maybe just to vary things, maybe take a little pressure off of me here, why don't we try spelling something else? This time a different 3-letter word, but maybe 8 volunteers. Could we get a byte's worth of volunteers? And I can sweeten the deal with some stress balls in exchange. You just have to be comfortable coming up on stage and being on the internet. So yes, 1, 2, how about 3, 4, how about 5, 6, 7, and how about 8? Come on up. A round of applause for our volunteers. Yep, come on. All right, so what I'm going to have each of you do is represent a bit in a particular order. So if you want to just in any order, line yourselves up here facing the audience. Come on over. All right, and we will have you represent, well, we got to see who ends up where. Scooch this way a little bit. This way, this way. All right, so you shall be the 1's place, and just hold that in front of you. 2's place, 4's place, 8's place, 16, 32, 64, and 128. And just compress yourselves a little bit if you could. So each of these folks represents a bit in a particular place. And let's say this. If you're just standing there sort of uncomfortably without any hand raised, we'll assume that you're representing a 0, quite simply. If your hand goes up, though, the audience should assume that you're representing a 1. And therefore, what we'll do is spell out a 3-letter word. And on each round of this, you'll either stay like this or you'll raise your hand. But first, let's actually meet some of our volunteers here, starting with position number 1, if you'd like to say your name, perhaps where you're from and or studying.
Hi, my name is Brooke. I'm from Indiana, and I'm studying biology and computer science.
Nice. Welcome.
Hi, I'm Becca. I'm from Maryland, DC area, and I'm studying electrical engineering.
Welcome.
I'm Addison. I'm from Maryland. I'm studying engineering.
Hi, I'm Sharon. I'm from Rwanda, and I'm studying CS and math.
Welcome.
Hi, I'm Grace. I'm from Alabama, and I'm studying electrical engineering.
Welcome.
Hi, I'm Angelina. I'm from Maryland, and also I stay in Matthews.
Nice, Matthews. Nice.
and I'm studying applied math and econ as well as environmental science and public policy.
Welcome.
I'm Owen Bells, and I'm from rural Virginia, and I'm studying CS.
Nice, welcome. And
my name is Max. I'm from London. I'm also staying in Matthews, and I'm studying computer science and neuroscience.
Welcome aboard as well. If you're wondering too why I was wearing these glasses at the start, so very common on the internet nowadays is these POV videos. So it turns out these Ray-Bans actually record video footage, and we have a couple of them, and we thought we'd offer them to a couple of volunteers if anyone wants to record their point of view for everyone here. And Vlad here is going to help make sure they're recording. Second volunteer? Yes, number 2. All right. So as Vlad gets those set, on the backs of your pieces of paper, you have instructions for the following 3 rounds. Each round represents a letter. The audience participation part of this is to actually do the mental math to figure out what number these volunteers are representing. So go ahead and execute round 1, either keeping your hand down or raising it appropriately. OK. What number are our volunteers here representing? 66, because we have a 64 plus a 2. That then maps to what ASCII letter? B was the first letter. OK, hands down. Round 2, go. A little harder. What's now being represented? I'm starting to hear it. 79 is in fact correct. 79 because we have a 64 and an 8 and a 4 and a 2 and a 1. So if it's a 79, we have the ASCII letter O. OK, so we've got B, O, and then lastly, third round, go. We have 0, 1, 0, 1, 0, 1, 1, 1. What number is this? 87, which spells the letter W, which spells the word, not bow. Take a bow if you could. All right, a round of applause for our volunteers here. And come on off this way and help yourself to a CS50 stress ball. Thank you to our volunteers. So this is only to say we've now agreed on how we can represent numbers from 0 on up. We've agreed on how we can represent letters, but at least letters using ASCII. And in fact, these are more than just decoration. In fact, as a little bit of trivia by lecture's end, if you want to come up for your very own CS50 stress ball, turns out there's 64 light bulbs at the foot of the stage here. If you break them down into 8-byte or 8-bit or single byte chunks, there's an 8-letter word that happens to be spelled out today using this here ASCII chart. So today's mystery is, what exactly is that there word? But of course, if you have only 8 bits, you can only represent like 256 characters, which sounds like plenty for English. And indeed it is. 0 through 9, A through B, capital and uppercase and lowercase, as well as punctuation. But there's so many other human languages in the world that have other characters. For instance, we have not just the English alphabet we might see here on a US English keyboard. We have accented characters. We have various Asian languages have even many more glyphs. We need more than 256 possible characters. And so nowadays, computers do not just use 7 or even 8 bits. They might use 8 bits for some letters, like all of the English letters. They might use 16 bits for certain other languages, maybe even 24 or 32 bits. And fun fact, if you have 32 bits, and we have more than that on the stage, if you've got 32 bits, you can actually represent as many as 4 billion possible characters, which is quite a bit. No pun intended. So what else can we represent? Well, the goal of this system, not just ASCII, but something known as Unicode, which is a newer standard, is to be backwards compatible with ASCII. So humans left all of those other numbers alone, 65, 66, 67, and so forth. But they added to it a superset of representations that maybe are 16, 24, or 32 bits. The goal being to be able digitally to represent all human languages, past, present, and future, and even through pictograms, things like smiley faces and the like, even people, places, things, and emotions that transcend human language. And in fact, odds are within the past few minutes or hours, most of you have used one or more of these here emoji, these pictograms, which it turns out are just characters on a keyboard. You might have to hit a special button to pull up that form of the keyboard, but these are just here characters. And so these emoji have exploded in popularity for a number of reasons, one of which is, my God, what are we going to do with 4 billion possible patterns of zeros and ones? We can start to kind of have some fun with it and represent things beyond English and human languages alone. Now, as an aside, when it comes to Unicode, it turns out Unicode, years ago, standardized this pattern of 32 zeros and ones to represent just one of those emoji. So emoji tend to use even more bits here. Anyone know what decimal number this is? This is not a fun mathematical exercise. The spoiler is 4,036,991,106 is the decimal number that actually represents, as of present, the most popular emoji in the world. Does anyone want to hazard a guess what emoji this here number represents? Hearts? No, but it's actually this so-called face with tears of joy. So perhaps think about the frequency that you send that one. And even though it's obviously a picture on the screen, sure, it actually is more like a font, because underneath the hood, it's indeed just a pattern of zeros and ones or a decimal number that the computer is storing. But the computer, be it Mac OS or Windows or iOS or Android, know to display that pattern as this here picture. But the pictures might look different depending on the hardware. Why? Because there's companies like Google and Microsoft and Meta and others that have their own artists on staff as employees, and those artists interpret the descriptions like face with tears of joy differently. So those of you with an Android phone actually see face with tears of joy looking a little something like this. And if you have Telegram, for instance, installed on your phone, it's even more animated than that. It's this here emoji using the same pattern of zeros and ones. So different artists render these here emoji in different ways, but all they are here are patterns. Now, for all of the other answers, save one that was shouted out a moment ago, this is a sort of cloud diagram of the most popular emoji as of a couple of years ago per Unicode, whereby the size of the emoji indicates its relative popularity. So heart, I did here over here, is indeed one of the most popular ones as well. Question? A really good question. Why do certain emoji not show up on one device or another? It depends on how recent the software is. Pretty much every year, the humans behind the Unicode consortium release new emoji, which is to say they decide that this other pattern will represent this new emoji. This other pattern will represent this new emoji. And unless you update your phone, your laptop, your desktop to the very latest software, and the manufacturer of that device or software also updates by hiring an artist to draw those pictures in their own font, in their own style, you're going to see usually just like an empty black square, or maybe just like a black and white heart instead of something more colorful, really just placeholders. Because it's as though you don't have the right font installed, or really you have an older version of that same font installed. But it's become sort of an annual tradition that new and more emoji are released every year, which is among the reasons why these updates contain more and more. Yeah? That is an amazing segue. How do you represent color in bytes? Well, you use RGB, which happens to be, by coincidence, the next slide. So let's again recap. We know how to represent letters. We know how to represent numbers. We can even represent emoji. But those emoji, technically, on the screen are, of course, composed of colors, like a whole bunch of yellow for that their smiley face. How do computers, then, using only zeros and ones, represent colors? Well, by convention, they typically use a system that, by an acronym, is called RGB, red, green, blue. And this is to say that a computer, to represent a single dot on the screen, maybe this one, this one, this one, will allocate some number of bits or some number of bytes to represent the color of just that there dot, otherwise known as a pixel. You can actually see pixels on your phone or even on your TV or monitor. If you go really close, especially if it's an older monitor, you can see the tiny little squares. Each of those has some number of bits telling the device what color to use. In particular, these devices typically use 3 numbers in total, 3 bytes. So that is to say 24 bits per pixel. And they do this. If you were to represent a single dot on the screen using these 3 numbers, just by intent here, this is 72, 73, 33, which in the context of a text message, an email, a Google Doc, represents, of course, high. Textually, what if a computer uses that same pattern of zeros and ones, that is, the same pattern of decimal digits, to represent the color on a screen, which is germane if you're opening an image using Photoshop. So using a different piece of software that knows about colors and images and not just text. Well, this would imply that you want that dot on the screen to have like a medium amount of red, a medium amount of green, and a little bit of blue. Why do I see medium and little? Well, again, if each of these numbers is using 8 bits, or 1 byte. The highest we can count, as we discovered, was 255. So I'm kind of averaging here. So 72 out of 255 feels to me like a medium amount of red. 33 feels like relatively little blue. But if now the computer combines those wavelengths of light, so to speak, a medium amount of red, medium amount of green, a little bit of blue, what you get is the color code for a single dot. And does anyone want to guess what color roughly this represents? These 3 bytes? Not white, not purple, not brown. Yellow, in fact, is the answer. So it represents in a single pixel roughly this shade here of yellow. Which is to say, if we look back at any of those emoji, which again are represented by patterns of zeros and ones, but you and I as humans perceive them as images on the screen, let me actually go ahead and zoom in further to one such sample emoji. And when you zoom in far enough, or you put the phone close enough to your face, you can actually see all of those little dots known as pixels, all of the little squares. And given that so many of these pixels are yellow, that is to say that that pattern of 3 bytes, 72, 73, 33, is used to represent this pixel. Another 3 identical bytes are used to represent this pixel, this one, and so forth. So now if you've taken digital photos on your phone or a camera, you're probably generally familiar from the internet and hardware today that a photograph is what, like 1 megabyte, 10 megabytes, depending on the resolution of it. Well, megabyte means millions of bytes. Where are all of these bytes inside of these photographs or these images you're taking or downloading? They correspond to every one of the single pixels on the screen. There's at least 3 bytes being used to represent every one of those dots. As an aside, bit of a white lie, because nowadays there's fancy compression software that can use fewer than that many bytes. But in general, that's where all of those bytes, those millions of bytes, are coming from. So how was that for an answer to how do we represent colors? Thank you. So if we agreed now that there's this way and perhaps others to represent colors, well, how do we represent not just images but videos? Well, videos, once upon a time, or movies, were called motion pictures. So pictures with motion. Why is that? Well, it's analogous to growing up. If you ever played with one of these picture books, and in fact there's memes nowadays that have made these popular again, whereby you have a whole bunch of images on individual sheets of paper, and if you flip through them fast enough, your human mind and eyes perceive it as actual motion, even though you're just seeing image, 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 but it's so fast it looks like motion. That's all a video is on your screen. That's all a film is on your TV. It is not, in fact, continuous motion. It's maybe 30 frames or images per second, maybe 24 frames or images per second, which is to say we know how to represent numbers, we know how to represent letters, we know how to represent colors and thus images. Now we kind of get videos for free because it's just more of the same. Use more and more of those patterns. Why are videos so darn large? Why are they gigabytes to download? Billions of bytes? Because there's so many darn images, 30 some odd images per second in those kinds of videos. And maybe lastly, just to top off our multimedia, how could you represent sound? Maybe musicians in the room, how using only zeros and ones could you represent something as sonorous as music? Something analog as digital, yeah. Yeah, so each number that we store in the computer could correspond to a certain frequency, which has a direct relationship to the sound or the pitch of a note. For instance, in the world of piano and many other instruments, you've got like your A, your B, your C. Maybe you have sharps and flats as well. We could just agree, like the ASCII people did years ago, to represent the musical note A, let's use this pattern. Musical note A sharp, let's use this pattern, and so forth. But maybe pitch alone or frequency alone is not enough. Maybe we need that number, but maybe a second number for the volume, the sort of digital equivalent of how hard are you hitting the key on the piano. Maybe a third number for how long are you holding the key down. So maybe the pitch and the volume and the duration, kind of like RGB, we could use 3 bytes to represent every musical note in some piece. And if we wanted to keep track of what instrument should be played by the computer to sound that music, well, maybe that's just a 4th byte or something else as well. Which is to say, at the end of the day, all we have are these zeros and ones to throw at the problem.